Hello everyone, myself Madhuri Modak, Assistant Professor in Mathematics, Department of Computer Science, Abhidayanangar Senior College. In the subject Mathematics, Groups and Coding Theory is very important paper. Now in Groups and Coding Theory, already we have seen the first unit. Now we start with the second unit, that is Groups. Now we have seen how to show certain set G with respect to star is a group in case of finite and infinite set. Now the next point is elementary properties of group. First is uniqueness of identity. In a group G, there is only one identity element. So it means what? If you consider any group G with respect to any binary operation, then there exists one and only one identity element in that group. Now, whenever we have to show uniqueness in mathematics, generally we consider two such things exist and then we show that these two things are not different but they are same. So in same way, we consider here there are two identity elements, say E and E dash in a group G. Now, as E is the identity element in that group G, by definition of identity element for any element A in G, we can write A star E equal to A. Actually, A star E equal to E star A is equal to A. So, we are considering the part that A star E is equal to A by using definition of identity element E. Now, as this is true for all elements say in G, it is true for E dash also being an element of G. So we put A equal to E dash here. So E dash star E is equal to E dash by putting A equal to E dash. Now, E dash is also an identity element in group G. So, by using the definition of identity element, we get A star E dash is equal to E dash star A is equal to A for all A in G. But we have written only second part of that definition, that is E dash star A is A, which is required in this case. Now, as this is true for all elements A in G, it is true for A equal to E also. So we can write this equation by replacing A by B, A by E. So we get E dash star E is equal to E. Now see first and second equations. If you observe their left hand side, they are same, that is E dash star E. So as left hand side are equal, we get E dash equal to E. It means the two identity elements E and E dash are not different but they are same. So in any group G, the identity element is unique. That means there is one and only one identity element in any group G, which is very important property of group. Now, next theorem is cancellation laws. Now, in arithmetic also, we have seen cancellation laws in school that for real numbers A, B, C, whenever A plus B equal to A plus C, we get B equal to C. That is left cancellation law. Similarly, there is right cancellation law also. So, in group also, there are left and right cancellation laws. Let G be a group and A, B, C be elements in G. Then B star A equal to C star A implies B equal to C. So here we are cancelling A from both the sides, which is to the right of star. So this law is called as right cancellation law. Now second law is A star B equal to A star C implies B equal to C. So here we are cancelling A, which is on left of star. So cancelling A from both sides, B equal to C, which is called as left cancellation law. Now we prove both the laws. Now in first part, it is given that B star A equal to C star A and we want to show B equal to C. So we start with B star A equal to C star A. Now as G is a group, every element has inverse. So definitely A has some inverse because A is an element of G. So consider A dash as inverse of A. Now post multiplying by A dash we get. Now post multiplying by A dash means we are multiplying on left hand side and right hand side by A dash, but after B dash, B star A and C star A. So post means after, and if we are multiplying pre, then it means before that term. So by post multiplying by A dash, we get B star A dash is equal to C star A dash. Now as G is a group and all are members of G, we can use associative property of star. So left hand side we can write as B star in bracket A star A dash. Similarly right side is C star in bracket A star A dash. Now here B star one bracket is equal to C star some bracket, but see here in bracket it is A star A dash and here also it is A star A dash, means both elements are same which are present to the right of star. So we get B star E is equal to C star E. Why? Because A star A dash is identity, as A dash is inverse of A. By definition of inverse, A star A dash is equal to identity. So for both the brackets we write it as E. Now by definition of identity, B star E is B and C star E is C. So finally we got B equal to C. So starting with B star A equal to C star A, we reached at B equal to C. So this law is called as right cancellation law. Now similar way we prove left cancellation law. Now in left cancellation law it is given that A star B equal to A star C and we have to show B equal to C. Now start with A star B equal to A star C. Again as A is an element of G and G is a group, A has some inverse. So we consider A dash as inverse of A. Now pre-multiplying by A dash. Now remember pre-multiply means we are multiplying each term on LHS and RHS by A dash taking it before that term. So A dash star A star B is equal to A dash star A star C. Again similar to previous theorem, by associative property of group, this is A dash star A star B, which is equal to A dash star A star C. Now as A dash is an inverse of A, by definition of inverse, A dash star A is identity. So it is E star B equal to E star C. Again by using definition of identity we get this as E star B as B and E star C equal to C. Thus we get B equal to C. So from A star B equal to A star C we get B equal to C. This law is known as left cancellation law. Thus, we have shown that in any group G, left as well as right cancellation laws hold. Now, similar to uniqueness of identity, in every group there exists one and only one inverse for every element. See what is the difference. In entire group, identity element is unique. And in case of inverse, for every element, inverse may be different, but the inverse of each element is only 1. So if A1 is an element, its inverse is B1 and that element is unique. Similarly for A2, inverse is B2 and again that element is different, which is unique element for A2. In this way for every element in group it has unique inverse. See the statement, let G be a group and let A be an element in G. Then there is a unique element B in G such that A star B equal to B star A equal to identity. That is, every element in a group has unique inverse. Now, similar to proof of uniqueness of identity, to show that each element has unique inverse, we consider that that element has two inverses and then we show that they are same, not different. Suppose that B and C are both inverses of A. Finally, we show that B and C are equal. Now, as B and C are inverses of A, by definition, A star B is equal to B star A is identity. Similarly, as C is an inverse of A star C equal to C star A is equal to identity. Now see the rightmost side of 1 and 2. It is E. It means A star B, B star A star C, C star A all are equal. So we consider A star B equal to A star C. Now to the left of star it is A, here also A. So we can use left cancellation law as it holds in any group. So by using left cancellation law, we cancel A from both sides. We get B equal to C. So we have assumed that B and C, these are two inverses of A, but we got B equal to C. Hence, every element in a group has unique inverse. Now see this remark. For an element A in a group, there is unique inverse in G. Now we denote this inverse by A to the power minus 1. So this is the notation to write inverse of A. So A star A inverse is A inverse star A is equal to identity. And from this A inverse inverse is A. That means inverse of inverse is a element itself. Now, next theorem is known as Sauk-Schutz property. Let G be a group and A and B are elements in a group G. Then A star B inverse is equal to B inverse star A inverse. Now, here we have to show that inverse of A star B is nothing but B inverse star A inverse. So, whenever we have to show that B is an inverse of A, we have to show AB equal to BA equal to identity. So to show that inverse of this element is B inverse star A inverse, we show that A star B star B inverse star A inverse is identity. At the same time, B inverse star A inverse star A star B is also identity. So first consider A star B inverse star A inverse. Now we use associative of star because G is a group. So it is A star in bracket B star B inverse star A inverse. But B inverse is an inverse of B. So by definition of inverse, B star B inverse is identity. So this is A star E star A inverse. Now by using definition of identity, A star E is A. So it is A star A inverse. Again by definition of inverse, this is E. So we got this answer as E, which is an identity element of group. Now call this equation number 1. Now another part is B inverse star A inverse star A star B. Similar to previous case, by using associativity we get this B inverse star A star B. Now A inverse star A is identity. Again by using definition of identity, this is B inverse star B, which is identity. Now for equations 1 and 2, right hand side is same, that is E. So their left sides are also same. So A star B star this element is equal to same element star A star B, which is identity. So by using definition of inverse, inverse of A star B is equal to B inverse star A inverse.